We can divide atoms into two parts, the nuclei, the most massive part, and the electron cloud, the most reactive part. Now first things first, what is the electron cloud, why is it the most reactive, and why it's actually different? Well, the electron cloud is the part of the atom where all of the electrons reside. You can think of electron cloud as a volume in which all of the electrons exist. The electron cloud is the most reactive part because when atoms bond, almost all of the forces responsible are created by electrons. Mostly because of how far they are from the nuclei, how small the nuclei is, and because of how nicely they interact in subshells. You'll see soon. Now we've seen all of those nice animations, it's time to remember that we are entering the quantum realm, and there is no such thing here as position. No, that would be crazy. Instead it's filled with wave functions, probabilities, and uncertainty, which I will probably leave for the quantum physics video, but that's why electron cloud is a useful concept. Because even though electrons aren't really these balls that just orbit in empty space and it's impossible to pinpoint the position like in our big world, we can still limit their possible position to a certain volume. Everything I said so far would have an asterisk before it, but that's good enough. Alright, now we have a decent idea of what the electron cloud is, it's time to divide it into shells, which are just small parts making up the full electron cloud. Now these shells divide even further into subshells, and these subshells divide even further into orbitals, but we don't care about orbitals because they are too complex and not that useful for this basic video. Alright, so far we've got this. We have the electron cloud in which electrons reside, which is divided into shells, which are divided into subshells. Now it's time to add some math to the mix. But don't worry, it won't be a lot. It will be just these four simple equations, starting with the first one, 2n squared. This equation tells us how many electrons can a shell have, the maximum amount. N is really often called the quantum number, which sounds amazing, but in reality it just indexes these shells, from 1 up to whatever you need. Now we can fill this in with the equations to check how many electrons can these shells host. That was the first equation. Now it's time for the two, the n and 4l plus 2. N is really simple, it just tells you how many subshells does a shell have. So first shell has 1 subshell, second has 2, 3 gets 3, you get the point. Now L is a subshell number, it's a bit different because it starts at 0, but just like previously we can use it to check how many electrons can a subshell host. It's the same thing. And now it's time for the last equation, which could be a bit of an issue actually, because it tells us in what order we should fill these subshells. We start from the lowest energy states, going up to the highest, but wait, and what does it mean? Why should we start with the lowest energy and go up? So yeah, electron clouds. In order to explain energy in electrons, we'll use a ball, that's what we'll use, because this ball has potential energy, which basically means how much kinetic energy can get. So over here it has a lot of potential energy because if I drop it, it will, speed up. Now everything in the universe wants to get rid of as much energy as it can. And because of that, this ball will try to give away as much potential energy as possible. What does it mean? Well, it's actually really easily explained if we imagine a universe where that doesn't happen. So let's imagine a universe in which this ball will not give away all of its potential energy. It would look like this. Yeah, so I think you can see some problem there. This ball still has some potential energy to give, and because of that it's just floating in the air. That's why this doesn't happen in real world, because you see this ball still has some potential energy to give away, and because of that in reality this potential energy is right away turned to kinetic energy. That's how this works. And so in the exact same way, all of the electrons want to be on a subshell with the lowest level of energy. So it's kind of analogous to the electron dropping till the very end. Now when it comes to the filling order, it's actually really simple, but also very annoying to explain if not explained graphically. That's why I'm going to use this animation. You see, we start with the lowest n plus l value with the lowest n. As I said, sounds weird, but it's simple, it just looks like this, and we fill them in until every single subshell is full. That's it. Now that we know these rules, we can use them on something larger. Like Palladium, which has 46 electrons. Yes, that is a lot, but don't worry, rules are here, and you can use these rules to check what these electron configuration subshells would look like. Starting with 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5 5s2 and 4d8. That gives us 46 electrons, palladium. Now we can take this note from the lab and we can check that palladium actually has no electrons on the 5s shell and instead has 10 electrons on the 4d shell, because you see those rules aren't exactly rules, they are guidelines with many exceptions, and actually if you want to get accurate results you should use a complex set of differential equations from quantum mechanics. That's chemistry. Thank you everyone so much for watching and have a great day. Bye!